Let's start with something simple. A star burns. That's what stars do. They have done it for billions of years. They will do it for billions more. And the process is straightforward enough that we teach it to children. Hydrogen fuses into helium. Energy is released. Light travels outward. The star shines. Simple, stable, predictable. Now let's talk about what happens when it stops. When a massive star exhausts its fuel, it collapses. The outer layers fall inward with nothing to stop them. No fusion pressure, no heat, no outward force of any kind. Just gravity, pulling everything toward the center at a significant fraction of the speed of light. The collapse takes less than a second. In that second, something happens that our equations can describe, but our minds cannot genuinely process. The core of the star, a region that was previously the size of Earth, is compressed into a sphere roughly 20 kilometers across. 20 kilometers. You could drive across it in 15 minutes. And into that sphere goes the mass of a star. Not a small star, a star that was between 8 and 20 times the mass of our sun. The result is a neutron star. And from this point forward, almost everything you think you know about how matter behaves stops being true. Let's start with density, because this is where the logic first begins to break. The densest naturally occurring substance on Earth is osmium, a hard bluish-gray metal. Its density is roughly 22 grams per cubic centimeter. That means a cube of osmium, the size of a sugar cube, weighs about as much as a golf ball. Dense, impressive, completely irrelevant by comparison. A neutron star has a density of approximately 400 trillion grams per cubic centimeter. Take a moment with that number. Not to memorize it, to feel the gap between it and everything you have ever touched, lifted, or tried to move. The famous example is the teaspoon. A single teaspoon of neutron star material would weigh approximately 10 million tons. That is more than the combined weight of every vehicle ever manufactured by humanity. Every car, every truck, every tank, every ship, every aircraft, in a teaspoon. But here is where it gets stranger. Because density alone does not break physics. We can measure density. We can write it down. We can handle it mathematically. What we cannot handle is what that density does to the matter itself. Inside a neutron star, atoms do not exist. That sentence needs to sit for a moment. Everything you have ever touched in your life was made of atoms. The chair you are sitting on, the air in your lungs, your own body. The screen you are looking at right now. Atoms. Nuclei surrounded by electrons, held in structure by electromagnetic forces. Inside a neutron star, the pressure is so extreme that atoms are crushed out of existence. Electrons are forced into protons. The electromagnetic force, one of the 4 fundamental forces of nature, the force responsible for virtually all chemistry, all biology, all material structure, is simply overwhelmed. What remains is not matter as we understand it. It is a fluid of pure neutrons, packed together so tightly that they are essentially touching. No space between them, no structure. Just neutrons, wall to wall, in every direction, for 20 kilometers in every direction. A 2021 paper in Physical Review Letters, based on gravitational wave data from neutron star mergers, concluded that the matter in a neutron star core may be even stranger than this, potentially existing in a state called quark-gluon plasma, where even neutrons break apart into their component quarks. The paper's authors noted they could not definitively rule out the existence of matter types inside neutron stars that have no name in current physics. Let that land. Matter types with no name. Now let's talk about what a neutron star does to the space around it. Gravity on Earth's surface accelerates objects at 9.8 meters per second squared. That is the force you feel when you stand up, the force that makes falling dangerous. Surface gravity on a neutron star is approximately 200 billion times stronger than that. This is not a number that scales intuitively. So let's try it differently. If you were somehow standing on the surface of a neutron star, and you will not be, for reasons we are about to discuss, and you dropped an object from a height of 1 meter, it would hit the surface at approximately 7 million kilometers per hour. For comparison, the fastest bullet ever fired travels at roughly 7,000 kilometers per hour. Your dropped object would be moving 1,000 times faster than a bullet before it had fallen 1 meter. The object would not just hit the surface, it would release energy on impact equivalent to a nuclear explosion from a height of 1 meter. And the mountain problem. On Earth, the tallest mountain, Everest, rises about 8,800 meters above sea level. Mountains exist because the strength of rock is sufficient to hold that weight against Earth's gravity. On a neutron star, the same calculation produces a maximum possible mountain height of approximately 5 millimeters. The gravity is so intense that nothing can be taller than that. The entire surface of a neutron star is smoother than the smoothest ball bearing ever manufactured, because anything that protrudes more than 5 millimeters is immediately crushed flat. A perfectly smooth sphere, 20 kilometers across, containing the mass of a star, spinning, about the spinning. Before a star collapses, it rotates. Our sun completes one rotation roughly every 25 days. When it collapses, if it were massive enough, that rotation is conserved, compressed into something 20 kilometers wide. This is the same physics as a figure skater pulling in their arms to spin faster. The angular momentum does not disappear. It concentrates. The result is neutron stars that rotate hundreds of times per second. The record, as of current observation, is a pulsar designated PSRJ 1748-2446AD, which completes 716 rotations every second. Its equator is moving at approximately 24% of the speed of light. This is a solid object, 20 kilometers across, rotating 716 times a second, with surface gravity 200 billion times stronger than Earth's, with a magnetic field we have not discussed yet. Let's discuss the magnetic field. Earth's magnetic field is useful. It deflects solar wind. It makes compasses work. It is generated by the movement of molten iron in our planet's core. A neutron star's magnetic field is generated by the compression of the original star's magnetic field into a tiny volume. The same conservation law that speeds up the rotation concentrates the magnetism. The result is a magnetic field approximately 1 trillion times stronger than Earth's. 1 trillion. At that field strength, atoms cannot maintain their normal shape. The electron clouds that surround atomic nuclei, the clouds that give atoms their size, their chemistry, their ability to bond with other atoms, are compressed into thin cylinders aligned with the magnetic field lines. Chemistry, as a concept, does not function near a neutron star. The atoms are the wrong shape for it. A 2019 study in Science modeled what hydrogen atoms look like in a neutron star's magnetic field. The atoms become roughly 200 times narrower than normal and elongated along the field axis. The authors described them as looking like needles rather than spheres. Needle-shaped hydrogen. In a universe where we learned hydrogen was a sphere. And those magnetic fields are not static. They pulse. They rotate with the star. And as they rotate, they sweep beams of radiation, radio waves, X-rays, gamma rays, through space like a lighthouse. We call these pulsars. And we have been detecting their pulses since 1967, when Jocelyn Bell Burnell first recorded a signal so regular, so mechanically precise, that the research team briefly considered the possibility it was artificial. They nicknamed the signal LGM1, Little Green Men. It was not little green men. It was physics, operating in a regime so extreme, it looked designed. Now, let's talk about what happens if a neutron star comes near us. Not on a collision course, not impact, just near. Near, in astronomical terms, means within a few light years. At 10 light years, a highly magnetized neutron star, a magnetar, would be capable of stripping the ozone layer from Earth's atmosphere through gamma-ray and X-ray bombardment. Life on the surface would be exposed to radiation levels lethal to most complex organisms within months. There are no magnetars currently within 10 light-years of Earth. The closest known neutron star, RxJ 1856.5-3754, is approximately 400 light-years away. Comfortably distant. For now. But here is the calculation that changes the feeling of that comfort. In our galaxy, there are an estimated 1 billion neutron stars. 1 billion. Most of them are old, cold, and no longer pulsing. Invisible. We cannot detect them. We do not know exactly where they are. We know roughly where the pulsars are, the ones actively broadcasting. There are about 3,000 known pulsars in our galaxy. The others, the dark ones, the ones that have cooled below detection, are distributed throughout the galaxy in positions we can only estimate statistically. 1 billion invisible objects, each one 20 kilometers across, each one containing the mass of a star, moving through the galaxy at speeds of hundreds of kilometers per second. We are not tracking them. We cannot track them. And the galaxy is large enough that the probability of a close encounter in any human timescale is very small. Very small is not zero. Let's return to where we started. A star burns. Simple, stable, predictable. And then in less than 1 second, it becomes something that crushes atoms out of existence, spins hundreds of times per second, bends space around itself, generates magnetic fields that deform the shape of matter, and preserves inside its core a state of matter we do not yet have words for. Everything we know about physics still applies near a neutron star. The equations work, the predictions hold. But the regime is so extreme that the same rules produce outcomes that look like violations. Atoms cease to exist. Chemistry breaks. Mountains cannot grow taller than 5 millimeters. A teaspoon of the surface outweighs the entire human industrial output of the last century. The rules are intact. Reality, however, looks nothing like what the rules suggested it would. That is what a neutron star is, not an exception to physics, a reminder that physics contains rooms we have not yet opened, and some of them are not built for anything we recognize. Here is your question for the comments. A teaspoon of neutron star material. A single teaspoon. If it appeared on Earth's surface, not impact, just appeared, what do you think happens in the first 10 seconds? Leave your answer below. Next video, we go somewhere the neutron star's gravity leads us, into the objects where even the neutron structure fails, where the math produces an answer physics refuses to print. Black holes, but not the version you have seen before. See you there.